joining us again for the ribbon cutting ceremony of the Dave Heiner Community Diner. Come on in.
And take a seat.
Good afternoon, ladies and gentlemen. Thank you again for attending the very first session of the Dave Heiner Community Diner. Every month, just like a normal diner, we're going to have specials. Okay, maybe normal diners have them weekly. We're watching the cash flow. We're going to have them monthly. So this month, our specials are flow measurement. First thing that you have to understand with flow measurement is the universal flow equation. In the universal flow equation, in which Q equals A times V, Q is flow. Q could be flow in millions of gallons per day, gallons per minute, liters per hour, whatever your increments of measurement are. Area is area. A is area. And again, the area could be in square inches, it could be in square feet, whatever your measurement of area is. And V is velocity. And in our world, predominantly, velocity is feet per second. It is essential at our wastewater treatment plants, drinking water facilities, and industrial facilities to accurately measure flow. Flow is related to the efficiency, the effectiveness of the water treatment processes. It's also related to the quality of the product that we produce. That quality could be fuel for your automobile. That quality could be related to baby formula. Whatever the industry is, flow measurement and keeping the proportions of constituents and additives is extremely important. And of course, on a more simpler vein, when we get our gasoline or when we get home oil fuel delivered for our oil furnaces, that flow is measured, of course, too, for billing purposes. That flow is measured volumetrically. Our first manufacturer that we're going to speak about is Teledyne ISCO.
My name is Rich Skradsky, and I'm the regional manager for Teledyne ISCO. On behalf of Teledyne ISCO, I would like to welcome everybody to the inaugural Dave Heiner Community Diner Lunch and Learn. These are interesting times we are living through as we search for new ways to stay connected to our friends, family, and our industry. We are proud and pleased to support this month's Community Diner and trust that you'll find today's presentations to be both helpful and informative. Before I go, I'd like to thank all our essential water and wastewater professionals who have continued to keep our vital water and wastewater infrastructure working without interruption during these challenging times. Thank you, stay safe, and enjoy.
Teledyne ISCO are specialists for many, many decades, at least 4 decades, in open channel flow measurement. Open channel flow measurement is really one of the hardest flow applications to measure. The other being non-full pipe flow measurement, which can be treated as open channel flow measurement, and we can talk about that later. The ultrasonic measurement technique involves a non-contact sensor sitting above the surface of the water that emits a pulse down to the surface of the water, in which an echo is sent back, and the amount of time, the differential, all of that relates to what that level of the water is. And we know the geometry of the channel if it's a rectangular channel, so therefore we know the area, and with the ultrasonic measurement technique, we can now find out the velocity, therefore we can calculate the flow. Another true and tried method is the bubbler technology. Bubbler technology simply utilizes differential pressure. The flow meter has an integral compressor storage chamber, and it discharges a pressure in the form of a bubble to the flow stream, to a primary device. And that frequency of that bubble is about 1 to 2 bubbles per second. And by seeing that pressure, that the pressure transducer back in the flow measurement device sees, again, we can figure out the level of the water. Bubbler technology has been used for decades. I find it to be very repeatable. Area velocity is another very popular flow measurement technique. This is a contact measurement technique in that an area velocity sensor that both measures the level above the probe with a pressure transducer, and it also measures the velocity with a ultrasonic measurement device. That allows us to calculate the area, the velocity, and of course, Q, which equals A times V. Area velocity does have its limitations, and limitations include you must have a level of water flow that's above the height of the area velocity sensor, and you do compromise a little bit of accuracy, because most of the time this is used in a non-primary device application, that being just a partially full pipe. The last measurement technique that you can utilize is the Manning formula. The Manning formula is very popular if you do not have a primary device. This picture would lend itself very well to an H-flume at the end of that pipe, which would improve accuracy enormously. But since that doesn't exist, what we need to do is use the Manning formula. In this specific application, we would look at the materials and construction of the pipe, the geometry of the pipe, the flow restriction in the pipe if it's corrugated piping. But more commonly, you're going to use that in open channel flow measurement, like in streams or even rivers. The Manning formula requires you to do data points across the width of the flow element, be it a stream or be it a culvert or be it a channel. And then you can calculate what your flow is after you have those data points and a level. This can be done permanently. On the left, you see the ISCO signature platform, which is basically a plant monitor in that it can accept up to 8 inputs, be they Teledyne ISCO or be they anything. So anything you'd like to log, you could do it on that. The device on the right is the 2100 series, also from Teledyne ISCO, which is used as a flow logger when you're doing inflow and infiltration studies. ISCO has taken the ultrasonic flow measurement technique to another level by setting a new standard in open channel flow measurement, a standard in an application that's not so standard. The laser flow probe emits a ultrasonic beam, as we saw in the earlier slide, down at the level of the water. We measure back that level based on that. In addition to that, the laser flow emits beams down into the flow of the water at 15 different points. Now, there's a little bit of artistic license done in this slide, in that we don't go down to the center of the channel flow. Suffice it to say that we go down about 12-15% into the depth of the water. But as you can see, velocities are varying all over that flow stream. So a multi-point, multi-depth velocity measurement will give you the highest degree of accuracy. Again, we can do this on a temporary, a portable, a I&I study with the 2100 series, or we can do it permanently at your plant with our signature platform. Laser flow advantages are quite substantial. The advanced laser velocity measurement, multi-point subsurface velocity measurement, 15 different points, 3 different levels. It is the only non-contact flow measurement system that reads below the surface. It is extremely precise and accurate. It's easy to install and maintain, and we can even do submerged flow measurement as an option if you're involved in flow measurement in a line where you're accessing through a manhole and occasionally that manhole becomes surcharged. Very flexible platform with the 2100 series and the signature platforms. We're also very pleased that Teledyne ISCO is playing a very important part in the collection of samples to plot the COVID virus and to track it in our wastewater treatment facilities. This gives microbiologists the opportunity to have a real-time sample that's preserved to their requirements to be analyzed for the COVID virus. It's been very helpful in tracking and trending. Ladies and gentlemen, it is our privilege to introduce Benoit Boudoir, owner and CEO of Madelabs Technologies. Benoit is an inventor at heart, and he offers volumetric flow meters with real-time analog output. His products also include and are focused around advanced motor and pump performance analysis. Ladies and gentlemen, Benoit.
How to decrease the cost of operation of lift stations. I made a lot of volumetric flow meter during my lifetime. One of them made me discover that 1/3 of lift station had daily intermittent electrical problems that were affecting volumetric flow calculations. Later on in my life, I continued to develop other products, and one of them made me discover that 1/3 of electrical equipment had intermittent electrical problems. So one thing I've learned with this one is that electrical problem degenerate to the point where they can be discovered. When we calculate flow, you need to compensate for abnormal behavior. It's not just volume divided by time. That would be what I did back in the early 1980s. So you have to do something different when you want to compensate for abnormal behavior and if you want to have high accuracy. One thing I did not too long ago, I decided to analyze pumps within over 150 lift stations just to figure out when there was a difference in pump capacity, what was the difference in pump run time, and arrived with a rule of thumb that for every percentage difference in pump capacity, you had twice that difference in pump run time. So if you can increase the pump capacity by only 5%, you will decrease the pump run time by 10%. The key here to be able to reduce the cost of operating a lift station, other than finding problem earlier, is that when the flow rate is low, run the pump at the highest possible level of operation within the lift station. When the flow rate is high, run them as low as possible. Don't wait to reach the lead level to operate your pump for 2 hours when the flow rate is high. Start the pump way earlier so it will take more time to get the lag level where both pumps start and the efficiency drops quite a lot. That's the solution. How to implement the solution? First, you need to have flow in real time, not at the end of a cycle for the cycle before. You need to have this in real time. It needs to be able to compensate for abnormal behavior, and it needs to be able to handle soft starts and soft stops. There are two things. If you can connect a level sensor, then it will also check if the level of operation are always the same, if it varies, or if you have any kind of abnormal behavior like level dropping without any pump running. This is the cheapest way of operating lift station, but usually it's because you have a siphon effect or the level sensor is defective. In both cases, it's bad. When you have a defective level sensor, it looks like something like this. This came straight out of a lift station with a SCADA system, top-notch SCADA system, that didn't discover anything abnormal in that lift station, by the way. Okay, even if all the pumps were starting together at the same time, like every 8 seconds for hours in a row, it was not enough to create an alarm. We have a test bed in Florida where we have a 7 lift station where they are analyzing data right now to see how much money they will be saving using a flow-based operating system. In their case, when the flow rate is low, they can increase as an average the level of operation of their pumps by 4.25 feet. In their case, the average increase in pump capacity because of the change of head is 17%. So increasing the pump capacity, that means it will reduce the runtime by about 34% when the flow rate is low, which is most of the day, by the way. By reducing the pump runtime by 17%, that means the electrical costs, maintenance, and wear of everything is down by 34%. I made a spreadsheet to help you calculate what kind of benefits you could get out of your own lift stations. You can download it from that small link that you have on the bottom here. I'll show you now how this device can be installed. Okay, in lift station, when pumps start and stop, of course they are using current, and which is proportional to the size of the pumps. With current, you know when the pump start, you know when the pump stop, you know how much electricity they are using. When the current start, that means the pump starts. When the current stop, the pump stop. If you know the volume between the start and stop level, you know the volumetric flow in and out of that lift station. If to the level sensor, then you will just check the level when the pump start and when the pump stop, and you will be able to calculate flow rate. In this case, what I'm showing right now is that to install this device, it's just a matter of putting 1 current lamps per pump. You just connect the device to a wall outlet, and the instrument is connected. And that's all there is. After that, you need to set it up. If you have a level sensor, we suggest to use a current isolator, and so you piggyback on that level sensor, and you'll have quite a lot of information out of this. As you might have noticed, there's different ways of installing this instrument inside a control panel. When you have a lot of lift stations and you don't have a lot of budget, I strongly suggest that you use it in your toolbox and you move it around. If you have a good SCADA system, make sure that it's working properly by cross-checking what you're getting using a device like this one. If you don't have any SCADA system, this can be just the heart of it. It doesn't replace a controller or anything like this, but it monitors perfectly what's going on inside the lift station. Usually it's a 45-minute presentation, so I hope you enjoyed that.
We hope that this has been helpful, informative, and another tool you can put in your toolbox for open channel flow measurement. Again, thank you for visiting the Dave Heiner Community Diner. See you next month.
That concludes our luncheon for today. I'd like to thank you all for attending. We look forward to hearing your feedback. Please join us for next month's luncheon.